So now we are going to do chapter 11 exercises. So I believe 7 exercises that are designed to be a review of chapter 11. So here we have one compound. It's called sulfone. We do not cover sulfones, and you don't. But to answer this question, you don't need to know what are sulfones. All you need to do is know that this sulfur here is tetrahedral, because these two double bonds are shown in the plane of the drawing. Ethyl group projects towards you, methyl group away from you. So is this compound R or S? And you need to show your work. So let's consider that. So if we go to answers, I can see, right? Okay, so the compound is S. You don't need to do italics on the test. So here we have 4 substituents. Oxygen, or 4 atoms directly bonded to chirality center. Hopefully you identify the chirality center as sulfur. So we have 2 oxygens that obviously have higher priority than 2 carbons. So oxygens are going to be priority 1 and 2, and carbons priorities 3 and 4. Now, when we consider first oxygens to determine which one is going to be priority 1, priority 2, one is oxygen 16, the other one is oxygen 18. So oxygen 16, heavier isotope, has higher priority. So that means that substituent with priority 1 is, here's the answer, yeah, is oxygen 18. So on the test, you would simply type, for example, 1, oxygen 18, and then 2, oxygen 16. And that indicates that you are assigning priorities 1, 2, and so on. And then priority 3. Now we have 2 carbons. That's a tie. Same priorities. When you look at the next atom of the highest priority attached to each of those 2 carbons, here we have carbon versus hydrogen. So carbon higher priority, hydrogen lower. That means this ethyl group, CH2, CH3, that's priority 3. And finally, priority 4 would be CH3. You don't need to type again subscripts, superscripts. Don't waste time on that. Alternatively, you can write it, let's say, oxygen 18-1, priority 1. And then I would use a semicolon. That's the best to understand that there is separation. Then oxygen 16-priority 2. And again, semicolon. Ethyl group, priority 3. And methyl group, priority 4. So those would be 2 ways that are 2 test answers that are acceptable. And then you would state that this is S, because substituent priority 4 is already behind the plane of the drawing. It's at the back. So you can ignore it. So 1, 2, 3 makes counterclockwise array or S. And so that's complete answer, stating that this is S and that the order of priorities of substituents. So that you didn't guess S accidentally, that you didn't get accidentally correct answer, or sometimes students make 2 mistakes in determining priorities, and when you make 2 mistakes, then that one compensates for the other, and you end up with correct answer, even though you're completely wrong. Because making 2 mistakes is even worse than making just 1 mistake. So that would be question 1. Okay, let me see if there are any questions about this one. We just started, so okay, no questions. So let's go back to question 2. So question number 2: convert double bonds of the following substituent into virtual bonds and atoms. This is a kind of compound that we cover in the 2nd semester, early in the 2nd semester. This kind of compounds. This is a good living group. Sulfonate ester, sulfonic acid ester. Now you don't need to know that. All you need to do now is convert these double bonds into virtual bonds and atoms. Because this compound has heteroatoms, sulfur and oxygen, no carbons, and just like previous one, I intentionally selected sulfur as chirality center. And there are two double bonds. That could be a little bit confusing to some students. So that's why I intentionally selected that. It's actually an easy question, but simply because atoms are different from what you are used to, it may be a little bit confusing. So here are virtual bonds and atoms are shown in red, and virtual bonds are also shown in bold. So to convert each double bond into virtual atoms and virtual bonds, you redraw that bond as a single bond. And then on each atom of the double bond, you add one virtual single bond. That's shown here in bold. So here we had one sulfur-oxygen double bond. We are converting that into two sulfur-oxygen single bonds. One of them is from the existing double bond, and the other one we just draw that, shown here as bold. And same for oxygen. And then we had another sulfur-oxygen double bond. We repeat the same process. We convert it to a single bond, add another single bond on sulfur and another single bond on oxygen. At the end of each of those virtual bonds, we need to place an atom. And the atom is going to be what is at the other end of that double bond. So when we look at the sulfur-oxygen double bond, from the point of view of sulfur, at the other end there was oxygen. So at the virtual bond attached to sulfur, at the other end we are going to add another oxygen. For oxygen, at the other end of the double bond was sulfur. So at the end of each virtual bond is going to be sulfur. And we repeat that process one more time. Sulfur, at the other end of the bond is oxygen, so we add virtual oxygen. Oxygen, at the other end of the bond was sulfur, so we add virtual sulfur. And that's it. So that will be complete answer. Now in this case, because for this coming exam, you cannot do actual drawing, and you cannot upload files, you will not have a question like this. This would be a quite common question for my exams, except that now we are limited by technology, so you cannot do a question like this. But I may ask you at the end, as you will see from the next question, to apply that to answer some other questions. So you should practice this. You should practice how to do this. Practice converting multiple bonds into virtual bonds and virtual atoms. And that brings us to question number 3. Determine the order of priorities of the following substituents. And that also means that you should determine whether it's R or S. Of course, on the test I will state that if I'm asking you for R or S. But that's once you determine the order of priorities, then obviously determining whether compound is R or S should be trivial. So again, you can see a little bit complex substituents with atoms that you're not used to. So intentionally just making it, it's not a difficult question, it's just something that you're not used to. Also practice this, because this takes a little bit of time. Questions like these are not difficult, but they take a little bit of time, and on the test, of course, you're limited with time. So you don't want to learn how to do it for the first time on the test, because you won't have the time. You could learn it on your own, you could figure it out, but that would be if you had like 2 hours for the test, not 40 minutes. And so that's why you cannot leave that for the test. That's why you should practice this pen and paper and practice that before the test. And so for this compound, first convert each double bond into virtual atoms and virtual bonds. And I just showed you how to do it. So I'm not going to do it again. I just showed you sulfur. These are all sulfur-oxygen double bonds. And in this case of this substituent, we have one sulfur-oxygen double bond. Here we have two. And so this is one, this is the other. Each of them is converted to virtual atoms and virtual bonds the same way as before. Now that we have converted everything to single bonds, we can start assigning priorities. And you can assign priorities to these two substituents, carbon and hydrogen. Two sulfurs, that's obviously a tie. So you will have to work that out. But sulfur has higher atomic number than either carbon or hydrogen, so 2 sulfurs will be priority 1 and 2. Carbon atomic number 6, hydrogen atomic number 1, so priorities are 3 for carbon or methyl group and 4 for hydrogen. So these two we have to figure out. And so to figure out the order of priorities, we should identify on each sulfur the path of the highest priority. So for this sulfur, that's oxygen sulfur. Here we have just oxygen atom. To virtual atom, there are no substituents. So oxygen, and if there is competition with something else, this has priority 0. So that's the only time when hydrogen has higher priority. For example, OH, if you had OH versus oxygen, OH has higher priority because it's hydrogen versus nothing. So while we can't have dangling bond at which, so that bond where at the end there is nothing, we must have virtual atom. There is nothing that is bonded to virtual atom because these atoms are virtual atoms and we don't consider usual valence rules. For example, that oxygen has valence of 2 or something like that. That's unimportant in this case. This is just oxygen and there is nothing else bonded to this oxygen. So those are priorities 0. So that's obviously OS is higher priority than oxygen because you have sulfur versus nothing. And here we have oxygen carbon. That's higher priority than this oxygen, but sulfur is higher priority than carbon. So this is path of highest priority. So for the substituent here to the left, we are following this path. Bottom substituent, this is path of highest priority. Again, we have 2 oxygens, we just discussed that, that's lower priority, and oxygen CH3, that's lower priority, oxygen carbon, then oxygen sulfur. Here we have another oxygen sulfur path. So arbitrarily we choose one. These 2 paths are actually 2 identical paths of highest priority, so we just select one at random. And we can see that these 2 paths are the same. So again, we have a tie. When that's a tie, then on each sulfur, we look for the path of second highest priority. So for and that's shown here, substituent on the right, we have oxygen, carbon. So now we're ignoring path of highest priority. We dealt with that. We have oxygen, carbon versus oxygen. That's highest priority. It's actually oxygen, carbon, hydrogen. Here it's oxygen, sulfur. And so it's oxygen versus oxygen tie, sulfur versus carbon. That's higher priority. And so this is priority 1. Bottom substituent is priority 1. One on the right is priority 2. And this is Fischer projection. So vertical substituents are behind the plane of the drawing. We can ignore hydrogen, lowest priority substituent, because it's on a vertical bond behind the plane of the drawing, to the back. So priorities are 1, 2, and 3. That's counterclockwise, or S. Okay, so let's see. I noticed that some questions were popping out, at least one. Okay, why do we need virtual atoms to answer this? Couldn't we just say the double bond is higher priority than the single bond? There is a video that shows that that's not the case. I know that some tutors will do that, tell you that double bond is higher priority than single and triple higher priority than double. That's correct in about 60 or 70% of the cases. And we often like to give you the remaining 30 or 40% of the cases on the test. So don't make that kind of guess. Simple answer to your question is no. Double bond is not higher priority than single bond. That's why you have to go through virtual atoms and virtual bonds. Question number 4. How many isomers of 1,2 deuterio 1,2 ditretioethane are possible? So you need to know deuterio or deuterium is isotope of hydrogen, tritium is isotope of hydrogen, and simply what you do is you simply draw this compound and draw all possible isomers. The easiest way to figure that out is to draw Fischer projections. Fischer projections are really convenient for things like this. And so you draw all 4 possible isomers. You can decide which atoms you want to put on vertical bonds. In this case, we are not determining whether it's R or S. But if it's R or S, if you were determining that and you're doing it arbitrarily, you can, arbitrarily you can draw your own formulas, like in this case, 4 formulas, the way you want it. You would want to put lowest priority substituent on a vertical bond, like protium. H is protium. Remember that from the first chapter. Symbol H is understood default to be protium, isotope of hydrogen with only proton in the nucleus and atomic mass of 1. Deuterium has proton and neutron, atomic mass of 2. Tritium, proton and 2 neutrons, atomic mass 3. So if you have a choice, you want to, and in drawing formulas, you may want to put lowest priority substituent on a vertical bond if you're determining RS configuration. But in this case, you're not. You're just figuring out number of isomers. So when you draw these 4 formulas, we can figure out that you have trio. You see, identical substituents on the opposite sides of Fisher projection. You have 2 trio enantiomers. They are clearly not superimposable, because if you rotate one of them 180, it's not going to superimpose on the other. So we have 1 and 2 as a pair of enantiomers. Those are 2 enantiomers, and that's trio pair of enantiomers. But now when you look at erythro compound, that's actually identical compound. You have plane of symmetry going through the middle of it, and if you rotate either formula 3 or 4 180 degrees, you get the other formula. So that's actually 2 representations of the same compound. And so trio isomer is actually a mesoisomer. We can call it trio isomer or mesoisomer. Both are correct. So we have mesoisomer, and that's 1 isomer or 1 compound. So 3 and 4 are not 2 different isomers. Those are 2 formulas of the same compound. That means that we have total of 3 isomers. And so in this case, correct answer will be total of 3 isomers. Trio pair of enantiomers and mesoisomer, or pair of enantiomers and a mesoisomer. Total of 3 different isomers. That was 4. Question number 5. Name the compound shown below. This one is really easy question. Really easy. The only issue here is that students get confused. Well, first, students forget to name something, or get confused because we have both a double bond and the chirality center. So what do I do when I have both? Well, you name both. So you start by where a lot of students end up, and that's why answer is not correct, by simply naming this compound without indicating configuration. So the longest chain, and there is only 1 chain, 7 carbons, so it's going to be heptane. And it has double bond, so it's heptene. Double bond is between carbons 2 and 3, so this is 2-heptene. On, of course, smallest possible number to double bond. And then on carbon 4, you have chlorine, 4-chloro-2-heptene. As I said, a lot of students end here, and that's wrong, because you have to indicate configuration. And then what some students, then second most common mistake is that students either figure out that this is S 4-chloro-2-heptene, so they indicate S 4-chloro-2-heptene, or that this is E double bond, or E2, E 4-chloro-2-heptene, but not both. Actually, you have to state both. So double bond is easy to figure out that it's E, because 2 hydrogens are not shown, but when you are looking at priorities, on carbon 2, you have carbon 1 as substituent, or hydrogen. Carbon versus hydrogen, carbon has higher priority. On carbon 3 of the double bond, you have carbon 4 as a substituent, or hydrogen not shown, again carbon versus hydrogen. So 2 carbons, carbons 1 and 4, are substituents of higher priority, and they are on the opposite sides of double bond. That's E. And so E is, so this is E, double bond. Now, for the other configuration of the chirality center, that's carbon 4. Now we are looking at substituents. You may want to show hydrogen just to help you. So you may want to redraw it with a hydrogen. So you can see that substituents are hydrogen, chlorine, carbon, and carbon. So chlorine is priority 1, hydrogen 4, 2 carbons, a tie. And then if you follow this, in this case actually double bond will have higher priority, because if you follow highest priority, you keep going, and eventually this virtual carbon here of the double bond will be the difference. It's going to be virtual carbon versus hydrogen, and this is going to be higher priority. And so in this case, where this will not be higher priority, for example, if I put, let's say, oxygen here, or bromine, or chlorine, then substituent 3 single bond would be higher priority than double. If I put something else here. But anyway, as shown in this case, that's one of those 60-70% of the cases where double bond does have higher priority than single. But again, to figure it out, you should use virtual atoms, virtual bonds. So it's not difficult to just break this double bond. You place carbon here, and that's it. So order of priorities is 1, 2, 3, 4. We ignore substituent 4. Again, counterclockwise, I keep on coming up with S. So it's S. So in this case, we list it as Se for chloro-2-heptene. And I noticed the question, I was able to read while it flashed, whether it's important, whether it's Se or Es. It's not really important. Sometimes we will even list it for S2E or 2E for S. 4 is listed first, so we list S first, 2, then so SE. But it's not really important because it's obvious what S refers to and what E refers to. Okay, before I do question 6, let me check if there are any other questions, any other one that you know, okay. Question number 6 is very easy, but I want to give you a warning about question number 6. Name the compound shown below. So you should know how to name it. We did cover naming earlier, and some of you may consider this question to be unfair, but it's not, because you have to know how to name these compounds, and you have to use nomenclature throughout the course. So yes, while you learn it for the first test, you have to know it for all the subsequent tests, because that's nomenclature, and you have to be able to use nomenclature in the second, third test, final, and organic too. So you should recognize that this is cyclohexanol. So you name this as cyclohexanol, and then hydroxyl group of cyclohexanol is attached to carbon 1. So this is carbon 1 of cyclohexanol, and we don't list 1. And then we have methyl group. So smallest possible number to methyl group that we can give is 2. So 2-methyl cyclohexanol. And you can see that OH and methyl group are on the opposite sides of double bond. That's trans 2-methyl cyclohexanol. So really easy, and you should name it as trans 2-methyl cyclohexanol. It could be, of course, 3 if it were on carbon 3, 4 on carbon 4. 2 would also be here, and 3 also here. If they're on the same side of the ring, both up or both down, then it's cis. Now, UPAC nomenclature for cyclic compounds is not cis-trans, it's RS, because each of these is chirality center, and you should name it as R or S according to UPAC nomenclature. Now, I don't know how many of you would be able to do it, and how much time it would take. Probably a lot of time. Probably if I were to give you this and ask you which one is R, which one is S, the best bet, I'm not going to do it, of course, on the exam, but if I were to do that, probably the best bet for you would be to make a model and then work it from a model and so on. My guess is, to average student, it would probably take 20 minutes, and test is 40 minutes. So probably you would have, out of 27 questions, you would have to spend half a test on one, and would be left with 20 minutes for remaining 26 questions. I'm not going to do that. So if I see an answer like this, 1s2s2 methyl cyclohexanol, it's correct. There is no way you did it. Either you use the computer to get this answer, or you got somebody else, like a grad student, to do the test for you. So that's right away indication for me that this is not that's not your answer. So that's why I'm giving you this as a warning, as a fair warning, that this is really easy question. You should really be able to easily answer it as a cis or trans 2-methylcyclohexanol. But if I see answer like this, then I know that you're not doing it. Now, I may not right away assume that you are cheating, but I will want to talk to you. And once I talk to you, I may ask you to explain that and so on. And maybe, you may learn how to do it on this particular compound, but there is no way you can do it so quickly on if I give you another example or something like that. So, and that would be, as I said, that would be kind of treating that warrants F for the course. So that's why I want to give you fair warning. This is just one example. And of course, since I gave you this one example, I may not put that on the test. But there are other ways where I could ask question. It is really easy question. So just say this is trans 2-methylcyclohexanol. How long would it take? Like 1 minute to answer that. Trans 2-methylcyclohexanol. To figure out this is cyclohexanol and this is methylation carbon 2. Two of them are trans. Less than a minute, and just type it up. And that's, you should type this. So you would type this up, trans 2-methylcyclohexanol. And trans, you don't need to type in italics, just trans it, type it regular, trans type regular font. But as I said, questions like these, there are other alternative questions that don't look like this, but are other compounds, are simply for me to see whether you're using computer to generate answers, because obviously that's cheating. Computer, or if you're getting somebody else to do the test for you. Because you're doing tests online, and for a few of you who are taking tests here, I don't know about the rest of you, since you're sitting in a dorm at home. I don't know if somebody else is sitting with you or is doing tests for you. And so it's a question like this, because if somebody is doing tests for you, okay, I gave you this warning, and so you know this. But you don't know 5 other things, 5 other questions like this that I have ready. And so a person who is, let's say, a graduate student who may be taking this test for a student, that person doesn't know what I have covered in the class and what I expect. That person knows organic chemistry and can easily answer this. That and most of organic chemists have good tridimensional vision, that person can easily figure out just mentally rotate this, look at this, and say, oh yeah, this is S, look at this one, this is S, so 1S, 2S. In the same amount of time it would take you to figure out it's trans 2-methylcyclohexanol, that person would figure out it's 1S, 2S, 2-methylcyclohexanol. And so to that person, this is because that's somebody who is a graduate student who went through organic chemistry, then advanced organic chemistry, maybe physical organic chemistry, and who knows how many. And so something like this is trivial. That person has seen it so many times. That's just really easy. And so that person cannot really go back, kind of regress to level of introductory organic chemistry student and understand the difference between these two. So again, it's very important to me because I really don't want to catch anybody cheating. So that's why I want to give you so many warnings. Okay, and then question number 7 is very different in nature. And it's not a warning, it's just something you could encounter on a test for a change. Well, you could encounter this on the test, it's just that this question won't be on the test. It will be, if I do give you kind of question like this, which is partially a trick. It's not a trick in a sense, it's an easy question, and you should be able to easily answer it on your own and get points. It's a trick in a sense that if somebody else is taking the test, that person might be trapped. 7 is not a trick, but before that I want to see if there are any questions. Okay. Okay. So, okay, just a minute. There seems to be questions are popping up. So let me just see that. Okay. So if you don't specify UPAC nomenclature, we can just put cis-trans. In this case, I would not, now I told you this is UPAC nomenclature. In this case, I didn't even tell you what is UPAC nomenclature for cyclic compounds. And actually cis-trans for double bonds is UPAC nomenclature. That's a little bit odd, a little bit of quirk of nomenclature. That for double bonds, you can use, well actually EZ is UPAC, but we accept cis-trans. So, and UPAC calls it cis-trans isomerism. I would not have specified in question like this UPAC nomenclature because I didn't even tell you what is UPAC nomenclature. The only nomenclature I taught you was cis-trans. I didn't even teach you cis-trans for cyclic compounds, and I never taught you in this course. Remember that. Just think about that. I never told you in this course how to figure out RS on a cyclic compound. And so I wouldn't really ask that on a test. So yeah, it would be, so I wouldn't specify UPAC, but that's because I didn't even teach you how to do UPAC nomenclature on. I taught you only one. Okay, then, so for question 6, we don't have to include S and R. No, if you do include it, that's indication that you probably cheated and I would want to talk to you. You should put R and S. How do we know? Well, you should know, because if compound has chirality centers and you need to designate configuration, you should include R and S. In this case, you're designating configuration by including cis or trans, because in a cyclic compound, you have two ways to designate configuration, cis-trans or RS. And you were not taught in this course how to use RS, so the only way you can designate configuration is cis-trans. When compound is open chain compound, you cannot have cis-trans. If you have 4 different substituents on an atom, you cannot designate that as cis or trans. You can only designate that as R or S. If you have more than one chirality center, then you can designate that as erythro or trio, or meso or something like that. And that would be specified in the question. So for open chain compound, then sometimes there could be a difference. So for example, for open chain compound, sometimes if you have 2 chirality centers, I may ask for RS or erythro trio or meso, and then it will be clear. Then I will specify what I want. Okay, questions are a little bit popping up. I don't want to miss any. I hope I answered Victoria's question. So Helen, no, I answered Victoria. The next was Helen, so I'm getting a little bit lost because these things shifts when your questions pop up. Okay, so Skylar, just to be clear, if I accidentally name a compound like this with its chirality in its name, am I able to show my work to you? I won't get in trouble. I don't know how would you accidentally do it, because that's very advanced stuff. As I said, an average student would probably spend at least 20 minutes on that. So I don't know how would you accidentally do that. But yeah, odds are, if somebody did that, let's say if you did that, odds are you cheated. But I'm not going to give you F for the course right away. I would set up a meeting, and for any suspicion, because if somebody cheated, that's actually, I'm calling that cheating. That's actually suspicion of cheating, which means that first thing I would do is notify a student that I want to talk with that student. So then I would talk with that student, and if I establish, then I would allow student to explain that. Again, I won't go into details, but student will get an opportunity to explain the answer and so on. And then if after that I'm convinced the student cheated, then student would get formal notification that I believe that student cheated, and then the process, what is the penalty? Penalty could go anywhere from warning to F for the course. Certainly this would be F for the course. Warning is something much less. And then because the reason why this is F for the course is basically this is planning. Either you get somebody else to do it for you, or you use the computer program. That means you plan to cheat. Warning may be if somebody like kind of accidentally took an opportunity and wasn't really that important for the outcome of the test. So, but in any case, so student would get the opportunity to explain himself or herself, and then if I'm still convinced the student cheated, then I would write up a report that would go through committee and so on, and student would go to the committee, try to explain, and go on from there. So there is a process. Okay, so Andre, I use app on my phone to memorize different structures. One of the types they show is like the example you just showed, but they use RS in the naming. So if I were to identify one and put RS in my answer, is it still unacceptable? Well, yeah, because if you memorized RS, The best you can get, if you can convince me that you used RS because you memorized it, the best I can do is, if it's correct answer, is give you 0, because memorization is not 0 for that answer. That's the best you can get away for 0, because that's no, it's still unacceptable. Because as I said, to me, it's a tip-off that somebody is using a computer or somebody else doing test. So I keep on repeating that. So if you're using app on your phone is a variation of using a computer, and you're using that to get an answer. So that's unacceptable. Yeah. If you're working with private tutor, that's fine. But if tutor takes test for you, that's not. That's an F for the course. Or if tutor is with you when you're doing the test. So again, yeah. So those are all unacceptable things. Yeah. Okay, I think I answered all the questions. Are there any other questions before I answer the final one? Okay, so the final question is a little bit different in nature. So okay, so final question number 7. The literature value of alpha D for limonene is plus 125. A sample of limonene has alpha D value of minus 100 degrees. Calculate the optical purity and the amount of each enantiomer in the sample. So I didn't have time to type up the answer, so maybe I can do it right now. So optical purity is the actual amount. And now to calculate optical purity, you're looking only at absolute values. So it's 100. It's minus 100, you don't care about minus. It's 100 over literature value. For pure enantiomer, 125 multiplied by 100%. And 100 over 125, that's 0.8. And then multiplied by 100%, that's 80%. So optical purity is 80%. Now, how much of each enantiomer you have? Now, that's where this minus matters. Because rotation is minus, optical rotation is minus, that means that minus enantiomer is present in 80% excess. That's enantiomeric excess. That's what optical purity means. That means that remaining 20% is racemic mixture. And racemic mixture means half is plus enantiomer, half is minus enantiomer. And so that means 10% is plus enantiomer and 10% minus enantiomer. So in total, you have 80 plus 10, 90% minus enantiomer and 10%. So this would be your test answer. So on test, you would simply type it up like this. So if you are calculating optical purity for enantiomeric excess, signs plus minus don't matter. But if you are calculating amount of each enantiomer, then look very carefully at sign plus or minus, because sign of rotation, because sign of rotation tells you which enantiomer is present in excess. And make sure that you know calculation properly, because a lot of students, when they see 80%, they do calculation correctly, 80% is correct, enantiomeric excess. They answer, okay, it's 80% minus enantiomer and 20% plus. But no, 20% is racemic mixture, which means half minus half plus. and then you have to split that up and recalculate correctly. It's really simple, really trivial calculation, and you can use calculator on the exam. You still have one more day, one more class before the third test, and we'll be doing chapter 12, and I will be answering any other questions. Maybe if there is anything, video of practice test 3 is posted, and you have practice test 3. But if I find anything interesting, anything I want to emphasize, I will also cover that on Monday. So we still have one more day to practice. So if you end up with any more questions, you can ask them on that day. So, okay, that's it. Let me see. Stop recording so that this can process. Okay.